Hi, in this screencast I'm going to walk you through project 2 and give you some hints on how you may want to approach the project. This project is about Deques and Randomized Queues. So here is the PDF for the project. You can find a link to this PDF on the assignments page of the course website, and on that page you will also see a link to the zip file for the project. And when you download and extract that zip file on your computer, you're going to see a folder such as this containing these files in it. Okay, so the folder contains the starter files for the project. It contains runtest.py that you should be using to test whether or not your programs meet the input and output specifications. And then there is report.txt that should serve you as a template when you write your report for the project. Okay, so now let's walk through the problems in the project. So the goal of this project is to implement some elementary data structures using arrays and linked lists. Okay, and in this project you will also get to learn about generics and iterators in Java. All right, so the first problem is called Deque. And here you're supposed to implement a data type that models a double-ended queue or a deque. All right. Now, a deque is a generalization of a stack and a queue, and it basically supports adding and removing items from either the front or the back of the data structure. Okay. So what you want to do in this problem is implement an iterable data type called linked deque. Okay, in the file that's called linkeddeque.java, and you're supposed to use a linked list to implement the deque API, which is shown here. Okay, so let's walk through the API. So there's a constructor linked deque that does not take any argument, and the purpose of the constructor is to construct an empty deque. Okay, an empty double-ended queue. There is empty, which is supposed to return true or false depending on whether the deque is empty or not. There is the size method, which is supposed to return the number of items on the deque. There is add first, that takes a generic item and adds it to the front of the deque. There is add last, that takes an item and adds it to the end of the deque. There is remove first, that removes and returns the item from the front of the deque. There is remove last, that removes and returns the item from the end of the deque. And then, since this is an iterable data type, there is the iterator method that comes from the iterable interface that linked deque is supposed to implement. The iterator method is supposed to return an object of type iterator, which you could use to iterate over the items of the deque from the front to the end. Okay. Now the iterator returns an object of a type that implements the iterator interface. All right, and if you look at the starter file, you will see a private class inside of linked deque that implements the iterator interface, and hence provides an implementation for the has next and the next methods that come from the iterator interface. Okay. And then finally, the deque API supports the toString method, which is simply supposed to return a string representation of the deque. All right. Now, when you implement your data type, you need to make sure that you handle all the corner cases that are mentioned here. So remember to do that. And then your implementation should also meet the performance requirements that are listed here. Okay. So your implementation needs to support each deque operation in constant worst case time, and it must use space proportional to linear in the number of items currently in the deque. Okay, and then in addition, your iterator must support each operation in constant worst case time. Okay, so you need to guarantee these requirements for performance. All right, so now what I'm going to do is just give you some idea on how you may want to go about implementing this data type. Okay, so we're going to use a linked list to implement the deque. So our linked list might look something like this. It's going to contain these nodes, right? So let me just draw a few nodes here. So what we have here is a deck implemented using a linked list, and the linked list essentially contains 3 nodes here. So it's going to have some items. So let's call it I1 for item 1, I2 for item 2, and I3 for item 3, and then there are these pointers, a pointer from the first node to the second, from the second to the third, and the third one points to null. Okay, now we're going to maintain 2 pointers, one to the first node in the linked list and another pointer to the last node in the linked list. Okay, now so this particular kind of a linked list is not going to do the job for us, and I'll come back to that in a bit. Okay. So we're going to maintain 2 pointers, a first and a last, and the operations that the deck supports, such as add first and add last and remove first and remove last, can be implemented using this linked list with 2 pointers to the first and the last node. But the thing is, add first and add last, as well as remove first, can be implemented in constant time as it is required. Okay. But the trouble is, with this kind of a linked list, we cannot implement the remove last in constant time. All right. Why is that? Well, when we try to remove the last element from this linked list, so let's say we want to remove this guy, then what do we need to do? Well, we have to get rid of this node here, and we need to make sure that the previous node points to null, right? But the problem is, we don't have a handle to the previous node of the last node. We only have a handle to the last node. So if we want to get hold of the previous node to the last, then we have to traverse this linked list from the start all the way up to the last element. Okay, so that is going to be a linear time operation, an operation that is linear in the number of nodes that are in the linked list, and that violates the performance requirements, right? Because we want to implement the remove last operation in constant time, right? So that's why I said earlier that this particular type of a linked list is not going to help us meet the performance requirements, especially when it comes to the remove last operation. Okay, so what we want to do is consider a modified version of the linked list, where we not only maintain a pointer to the next node, but we also maintain a pointer to the previous node. Okay, so the second node ends up pointing to the first one. The first one points to nothing, so it's simply null, and then the third points to the second. Okay, and then the first one's the last one's next is simply null. Okay, so I'll put a dot there to indicate null. All right, so what we have here is what is called a doubly linked list. Okay, and this is the type of linked list that we want to be using in this problem here, and this will allow us to implement all it'll allow us to implement the remove last operation in constant time. Okay, and we can also implement the other operations such as add first, add last, and remove first in constant time. Okay, so if you look at the starter file for linked deck, you will see that there is a private class that is defined there, which is called node. Okay, and this is the representation of the linked list that I've shown here. All right, and this node class is going to contain a generic item, okay, that we want to be storing in the node. So let me call it item. And then it's going to contain a pointer to the next node. Okay, and it is also going to contain a pointer to the previous node. Okay, So this is what you will see in the starter file, and this is essentially a representation of the doubly linked list. Okay, so now, so what you want to do is when you implement your API, you need to make sure that the next and the previous pointers are adjusted as necessary. Okay, so so that's how you want to be approaching this problem. And once you have your code implemented, you should test it, and the way you do that is by running the command java linked deck. So that is essentially going to run the test client that I have defined in linked deck, and if your implementation of the data type is correct, you ought to see this output. Okay, exactly. All right, so that's problem one. So now let's move on to the next problem. So here you're supposed to implement a random queue, okay, which is similar to a stack or a queue, except that here the item removed is chosen uniformly at random from the items in the data structure. All right. So again, a random queue is similar to a stack or queue, but the item that is removed is picked uniformly at random from the items that are in the data structure. So what you want to do in this problem is create a generic iterable data type called resizing array random queue in the file resizing array random queue.java, and your data type is supposed to use a resizing array to implement the random queue API that is shown here. Okay, so here we are not using a linked list to implement this API, but we are using a resizing array. Right? Why resizing? Well, because some of the operations that you have in the API have to be implemented in such a way that the array is resized as necessary. That is either grown or shrunk as needed. Okay, so let's walk through the API. So you have a constructor that's called resizing array random queue. It doesn't take any argument, and it constructs an empty random queue. Okay, and then you have isEmpty that tests whether or not the random queue is empty. You have size that returns the number of items in the random queue. Then you have enqueue, which takes a generic item as an argument and adds the item to the queue. And then you have the dequeue method that simply removes and returns a random item from the queue. And then you have the sample method that returns a random item from the random queue, but it does not remove it. Okay, so it's different from dequeue. Dequeue will remove and return it, whereas sample will just return a random item. It doesn't remove it from the queue. Okay, and then random queue is also an iterable data structure, so you ought to implement the iterable interface and hence provide an implementation for the iterator method, which is supposed to return an independent iterator over the items in the queue in random order. Okay, so what this means is that if I try to get several iterators on the random queue, then each one ought to be able to iterate over the elements in random order, and the order has to be different for each of the iterators. Okay, so that's what we mean by saying independent iterator. Right, and finally the data type needs to support the toString method, which simply returns a string representation of the random queue. All right, so so here again, make sure that you implement the things that are listed in this section that's called corner cases, and you also need to make sure that your implementation meets the performance requirements. All right, so here your randomized queue implementation must support each queue operation in constant amortized time. Okay, and it must use space proportional to linear in the number of items currently in the queue. All right. So what do we mean by constant amortized time? Well, so when you look at these operations such as enqueue and dequeue, so here so in the case of enqueue, you will be inserting an item into the queue, but if the queue doesn't have a space for this new item, then you have to grow the array, right, that stores the item. Similarly, in the dequeue method, when the number of items in the queue is much smaller than the capacity of the array, then you need to shrink the array, right? So with these two operations, you need to make sure that you either grow or shrink the array, and then you need to make sure that you copy the elements from the old array into the new one, and so on and so forth. Okay, so those operations, so whenever you do that, those are costly operations. Okay, but in the event where you're not growing or shrinking the array, these methods are fairly efficient. They're actually constant time operations, NQ and DQ and so on. Okay, so when you average over all the operations that you perform on the random queue, then you get a constant time performance, right? And in the average sense, and that is what we call amortized constant time. Okay. So your implementation needs to support each queue operation and constant amortized time. All right. Now, let me just say something about the DQ method. All right. So here, if you want to guarantee a constant amortized time, you have to be careful with your implementation, because what are you supposed to do in DQ? Well, it's supposed to you're supposed to first sample an item. You're supposed to get a random item, right? And then remove it from the array and return it to the client, right? But you need to make sure that when you do that, you're not moving the items around in the array, because when you remove an item from the array, you create you have a vacancy there, so you should not be moving the other items to fill in that spot. Okay, because once you start doing that, then it's not a constant time operation. Okay, but it becomes like a linear operation in the number of items in the queue. So there is a clever way of implementing DQ that will guarantee constant time operation, and I'll let you guys think about that. Okay, so it's a fun exercise. All right, so that's that. And now, once you have your implementation done, you should test it, and you can run this command on the terminal, and that runs the test client that I have given you inside of resizing array random queue. And if your implementation is sound, then it ought to produce this result here exactly. Okay. So that's problem 2. So now let's move on to the last problem in the project, which is called subset. So here you're supposed to write a client program called subset.java that takes a command line argument k and reads in a sequence of strings from standard input using stdin.readString. And what the program is supposed to do is print out exactly k of those strings uniformly at random. Okay, so again, the program takes a command line argument k and reads in a sequence of strings, let's say n of them, from standard in, and then it's supposed to print exactly k of them uniformly at random. Okay, now you have to make sure that each item from the sequence is printed at most once. All right, so it should so the string should not be repeated. So each string can show up in the output at most once. Now you may assume that k is greater than or equal to 0 and less than or equal to n, where capital N is the number of strings that you read from standard input. Now the running time of your program must be linear in the size of the input. Okay, and then you're allowed to use only a constant amount of memory, right? Plus either your linked deck implementation or your resizing array random queue object of maximum size at most n. Okay, so feel free to use either the linked deck or the resizing array random queue to implement subset. Okay, but you can use only a constant amount of memory. Okay, and one of these guys of maximum size at most n. And now and as an extra challenge, you can try to limit the maximum size to k. Okay, so that's also a fun exercise to think about. Okay, so once you have your client program written, you can test it by saying Java subset 3. So here k is 3, and then I supply these input strings, right? And then the program comes back with G, I, and E. So these are essentially, strings picked uniformly at random from the input strings. And notice that they are not repeated. Okay, and then I run it again and I get F, D, and E, and here again I get 3 strings picked from the input strings, and they appear at most once. All right, and then if k is 8, then and if the number of strings that I supply is equal to k, so which is 8 in this case, then the program prints all of them. Right, it has no choice but to print all of them, but then they all come out in a random order. Okay, so that's that. Okay, so those are the 3 problems. So the files that you need to turn in are these guys, and then remember to write your report. And for that, you should be using the template that I have given you, and make sure you fill in all the sections here. So you need to tell me how long it took you to work on the project. Fill in these sections telling me how you approached each problem and any issues that you encountered and how you solved them. And then this one is an important section where you need to tell me about any help that you received from anyone. All right. And then finally, if you enjoyed this project and you learned something from it, please tell me about it in this section. All right. Okay, so that's that. Now going back to the write-up, the last few things that I want to mention are: do remember to test your programs by running run tests. Okay, again, if you don't specify any arguments, run test is going to test out all the problems. So for example, I could say Python run test, and it just tests all of the problems. You can alternatively test a particular problem, for example problem number 2, and it just tests that particular problem. And then do remember to check your program for style, and the way you do that is by running check style and the name of the program. So for example, subset.java. Okay, and then finally do remember that the reports shouldn't be too long. They shouldn't exceed 400 lines. Make sure they don't contain spelling mistakes, and also make sure that the lines don't exceed 80 characters. Okay, so that's that. All right, so that's all that I had to say in this screencast, and I hope you have fun working on this project, and I do hope that you learn something from it. All right, so all the best. Thank you.